Today we're going to talk about units and dimension. Units and dimension. So we have to first understand what are units and what are dimension. So if I have to describe something, for example a rod, I can describe its mass or length. Suppose its mass is 1 kilogram and its length is 20 meter. The units of this are, the units of mass is kg and the units of length is meter in SI system. So these are the units, which are something that defines a number that's kept in front of it. So if I just write 20, you don't know what it is. Even though if I say it's a length, you won't know what kind of length, how long, until I write meter, because I can also write 20 centimeter, which will mean a completely different thing. You can think of a 20 centimeter rod and you can think of 20 meters. How big is 20 meter compared to 20 centimeter? Or I can also have written 20 kilometer, which will be a lot longer than 20 centimeter. So you can't be sure when I just write 20. But generally, it's always taken as SI unit if there is no unit mentioned. But this is not a concrete fact, it's just a convention. Okay, now let's talk about dimension. Here we have kilogram, which is a unit of mass. I hope you know that. So since it's a unit of mass, the dimension will be m, because for mass it's m. Now here we can see meter. For meter is a unit of length, which means its dimension will be L. I hope it's clear. We will understand about them much more in further discussions. Okay, now the next thing we are going to talk about is types of fundamental quantities. Types of physical quantities. So first of all, we have to ask, what is physical quantities? So what are they? Physical quantities are anything that describe an object quantitatively. For example, I have taken a rod, the same example I'm taking as the last one. Suppose its length is 1 meter and it's 20 kilogram. The fact that it's 1 meter and it's 20 kilogram never changes. I can change the number and which would change the unit, but it does not change. For example, I could have written 20 times 1000 gram, because 1 kilogram is 1000 grams, and which is the same as 20 kilogram. So this is the very cool thing about physical quantities. Okay, so I could have also written 1 meter as 100 centimeter or 1000 millimeter, which would still mean the same thing, which is amazing. Because let's take an example of something which is not a physical quantity. Let's take a face. Okay, suppose I draw a face. I said this face looks good. Okay, I said it looks good. Some might say it looks bad. Some might say it looks ugly. But it does not, it varies from person to person. But whereas the length of this rod and the mass of this rod never changes. It always remains 1 meter or 20 kilogram. If I'm talking about mass, it's going to be 20 kilogram. If I'm talking about length, it's going to be 1 meter, which is all constant. That's the amazing thing about physical quantities. It helps to describe something, and when you describe it, everyone will know how it is. Okay? So now, let's talk about its types. So we talked about physical quantities. Now, let's talk about its types. So there are two types. The first one is fundamental, and the second one is derived. So we will also talk about them as well. The first one is fundamental quantities. Fundamental quantities. Quantity or quantities, okay? And so first of all, let's talk about them. The fundamental quantities are the quantities that can be only described by them. So they can't be described by anything else. For example, generally, mass, length, time are taken as fundamental quantities. I'm writing kg, meter and second for simplicity's sake. I could have also written mass, length and time. So why are they considered fundamental quantities? Because they can be useful for deriving other things, and they are very easy or very dependent on themselves, and they are defined by something which is always constant. Okay? But for example, if I write 1 kg or 20 kg or 20 meter or 26 second, these are the fundamental quantities, because kg can't be described, kg or mass can't be described by anything else. So it is defined on its own. So they are constants. For example, what I mean to say is 1 kilogram is a constant by which 20 kilogram is described, and 1 kilogram is described by nothing. Now you might think of a question. For example, let's say velocity is displacement over time. So you might say, can't I describe length by doing bt equals to d, which means velocity times time is distance? Yes, of course you can. So doesn't that mean it's not fundamental? You can ask that question. But why is it still fundamental? Because we decided to. So it changes from system to system. So there are multiple systems, and the most preferred one is the SI system, or which uses 7 fundamental units. So fundamental units are something that are described on their own, which means they are constants, they are some sort of constant, and which is always constant in the universe. And they are chosen arbitrarily, which are best suited and which are most common. Okay? So now let's talk about derived, the second type, derived quantities. From the word derived itself, you might understand what this entails. So, for example, we have a fundamental quantity which is 20 kilogram, we have 20 meter and 26 second. For example, velocity is displacement over time, whose units is meter per second. So, meter per second is a unit as a whole, but it consists of two units, which is the meter and which is the second, which are the fundamental quantities. Okay, units of fundamental quantities. So this means that it is a derived quantity. Let's take another example. Let's say power. The unit of power is known as watt. So you might think, since this is one word, or you can also write is that W, since it is a word or one word, you might think this is a fundamental quantity because there is only one word. But this is false, because watt is just the common name. The most common definition of power is rate of doing work, so it's W by T, and work is force times distance by time. So force is Newton times distance means meter per second. You can also write it as this, and still here you might think Newton is a fundamental unit. It's not. It's a unit of force. So it can also be written as fundamental quantity in terms of fundamental quantities, which is kilogram meter per second square, because the most common formula of force is F equals to ma, which is mass times acceleration. So mass is for kg, accelerations mean meter per second square. So when combining these, you can write watt as kg meter square per second square. Meter, I meant to say, let me write this clearly. What I meant to say is kg meter square per second cube. So this is the representation of watt in SI system in terms of unit. That's why power is a derived unit. Similarly, velocity is a derived unit. So now let's talk about 7 fundamental units, because I told there were 7 fundamental units, but I never explained which of them are fundamental and what are fundamental and what is not fundamental. So the 7 fundamental quantities. Also, I think I might have confused you a little bit, so let me explain it a quick. Something that's I think you need to know. So fundamental quantity is actually length, mass, time. It's not kg, meter and second. They are fundamental units. Okay? There's a difference. Unit and quantity are different. So in the above example of the rod, I said 20 kilogram and 1 meter. They are units. The quantities are mass and length respectively. Okay? Also in derived quantities, the meter per second and kilogram meter square per second cube or watt are not fundamental derived quantities. They are derived units. Okay? The derived quantities are velocity, power, etc. Okay, now let's talk about the 7 fundamental units. So the 7 fundamental units are pretty simple, and they help us to quantify our world. So first of all, I will write the quantity over here, then its unit over here, and the symbol of the unit here. So first of all, the first one is length. Length is used to measure the length. So I think I don't have to explain what is a length because it's a pretty simple concept. So for example, if I have a bed, a pencil, a pen, I can measure its length, or it is also known as height, width, depth, etc. The unit of length in SI system, I will be using SI system for the most part. SI system is meter and its symbol is M, M for meter. Okay. The second one is mass, and the mass will be kilogram, and its symbol will be kg. Okay. The third one is time. Its unit is second and is represented by S. The next one is temperature, whose unit is Kelvin and its symbol is K. So I think most of you must have heard the first three. Now the bottom four might be a little confusing, and I will explain them after I have written them. Okay. So electric current. The next is electric current. Its unit is ampere and its symbol is A. Next, luminous intensity, and its unit is candela and its symbol is CD. Next is quantity of matter, and whose unit is a mole and its symbol is MOL, mole. Okay, so let's talk about all of them. So the first thing you might already know is the length. For example, you have a height. You know that height probably in centimeter, feet, or meter. Those are the units of length. So you have a pretty good grasp on length. Mass, on the other hand, you might not have, because what you think of as mass is actually weight. So if I represent mass as m, weight will be m into g. So mass is the amount of substance, is also like amount of substance. You can kind of grasp which mass is greater or which mass is less, but you exactly don't have a grasp of a mass. Okay, but I think you also know mass pretty well. The next is time. I think time is pretty simple. You might have you have countdown 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here, it was a time. I was counting a time, but I was not counting in second, because a second is a lot slower than what I just counted. Or you might just go 1, 2, 3, 5. So that is also a sense of time, but it's not, because we are not using SI system. If I use SI system, it will be like 1, 2, 3, 4, and so on. So I think you might have a good grasp of time as well. The next is temperature. I think most people will be most familiar with Celsius or Kelvin. I mean Celsius or Fahrenheit, which are most used in thermometers across the world. But Kelvin is the SI system, and you will know why it's Kelvin, because it defines how temperature works. It defines the minimum temperature of the universe that can be obtained. It is theoretically possible, but it has not been obtained right now. The next one is electric current. The current that runs to your house, that runs to the wires, they are measured in ampere. Next is luminous intensity. For example, let's take a candle. The candle up close will be very intense, but as you go farther, the brightness dims down, which is measured in candela. In this chapter, we will not talk about candela. Candela will most likely not appear. The last one is quantity of matter. For example, you can say, if I have a glass of water, I can talk about how many molecules of water is in the glass. That to calculate that, we have to use mole. Okay? Also, we have talked about the 7 fundamental quantities. Now let's talk about two derived quantities which are very unique. So they are called supplementary quantities. Okay, so there are 2 of them, and I think one you know very well, and the other one you might not know. Okay, the first one is plane angle. The second one is solid angle, and its unit is radian. The unit of plane angle is radian, whereas of solid angle is steradian, and the symbol of plane angle is RAD, while for solid angle it's SR. Okay, so for example, let's say I took a line and I took two lines. So this angle is known as, this angle will be measured in radian or degrees. So radian is the SI system, in degrees it would be a common system. So if I measure it by radian, so I could measure that or this, it will be plane angle. The quantity I'm measuring is plane angle. Okay, if I'm measuring a solid angle, for example, think about a sphere. Okay, think about a sphere and think about its center. Okay, take your hands, make a ball, think about it. Okay, and think about its center, and suppose I take some circular part of the ball. So this circular path, imagine, take a ball, take a circular path. Now from the center, draw a cone type shape. Can you think of a cone type shape? I hope you can imagine this, right? So if you imagine this, you will see a cone and it subtends an angle, which is a 3D angle. It's not a 2D angle like this, it's actually a 3D angle. It will look like this. It's curved and it will look like this. So this is the angle which is measured, which is known as solid angle, which is measured in steradians. We will not discuss more about this in this lesson, but you must know what it means. Okay, now we talked about some units, we talked about some quantities. Now let's get to the main storyline of this chapter, which is dimensions. Dimensions. So what are dimensions? First of all, I will write the definition and some few points, then we will talk and discuss about them. Derived quantities. Derived quantities are formed with the help of, so you may write along with me if you are making notes, is derived with the help of fundamental quantities. We also talked about this because velocity is described as length over time. So by the help of fundamental quantities. So I think this is pretty easy and pretty understandable. The next one we are going to talk about is dimension. Okay. The power. So the definition of dimension, I'm going to write it out. First of all, let's write it, then we will talk about the power of the the power to be raised on fundamental quantities in, so let me erase this quantity, I didn't write it well. So okay, once again, the power to be raised on fundamental quantity in order to represent given quantity is called dimension of that quantity. Okay, let's talk about it. So I will read it again. The power to be raised on fundamental quantities in order to represent a given quantity is known as dimension of that quantity. For example, let's take length. Okay, length. If I take length, in order to represent it as a dimension, I will just have to write L, because length is represented by L, and the power 1 because length will be meter, so it will be 1. Okay, so I will give you something that's not a fundamental quantity, because fundamental quantities are pretty easy to represent. So for example, let's take force. Force is, the most common definition you will find is force is mass times acceleration. Okay, so I could write acceleration as velocity per time, and I can also write velocity as displacement over time. So I could arrange this as m d t minus 2. If I change this d to L, which will represent length in this case, So it will be mass times length times t minus 2, t meaning time. So when I have to represent the dimension, so I will make a box which signifies I am mentioning the dimension of force. It will be, so let's see, power raised to the fundamental quantities. Remember that, fundamental quantities. The fundamental quantities used here are mass, length, and time. So I only have to write mass, length, and time. For example, mass, length, and time. Okay? So now let's look at the power. There is only 1 meter, which means the power raised to mass is 1. For length, there is only L, so which means it's 1. For here, there is minus 2, which means the power raised is minus 2. Is it clear? So let's look at this. Force can be written as mass times length times t to the power minus 2, which means mass is being raised by 1 power, length is by 1, and time is by minus 2, which is why we wrote minus 2 over here. So you might have a question, why didn't I write ml above? You can actually write above. So for example, I can write this as m l t. So this would be 0 and this would be 1. Sorry, let me erase this. The length as 1 and this as 0. This is perfectly fine because this would be considered as 1, which means you don't have to write it. And the 7 fundamental quantities, for example, temperature, etc., are also included in this box. It's just that their powers are 0. For example, temperature will be represented by theta or K. I'm going to use K in this case, or theta, which will both will work. So both of them are raised by 0 power because they will, since length is not a fundamental quantity that depends on temperature or other fundamental quantity except length. Okay, now let's conclude this. So we found that the fundamental the dimension of force, so we can write thus the dimension of force is 1 in mass, 1 in length, and minus 2 in time. So you can see here 1 1 minus 2. So I also don't, it is not necessary to write 1, so I can also write it as this. So you might see, and when you're studying for entrance or something that is based on MCQs, most teacher will just write MLT minus 2, which is also a common notation, but the proper notation includes a bracket. Okay, now let's talk about the next topic, which is dimensional formula. So I hope you are understanding what I'm teaching right now. So dimensional formula. So first of all, let's write it. The expression that shows which fundamental quantities are involved and in what ways to form a given physical quantity is called dimensional formula. It's called dimensional formula. Okay, for example, so let's read it again. The expression that shows which fundamental quantities are involved in what ways to form a given physical quantity is called dimensional formula. So it actually means, so let me write it down. For example, so let's take an example. The dimension formula of force. The dimensional formula of force. So I can also write this as F in a box because F is typically for force. So I could write MLT minus 2. So this is the dimension formula of force. Okay? So we're just writing its dimension. Okay, now let's talk about the next topic, which is dimensional equation. Dimensional equation. So let's an equation. It's an equation that relates given physical quantity with its dimensional formula. With its dimensional formula is called dimensional equation. For example, I could write like this: F equals to mlt minus 2. So you might think dimensional formula and dimensional equation are the same, but they are not. Dimensional equation, for example, for dimension formula, it's generally only one variable. For example, I could write like this, v. But in dimensional equation, I could also write like this, ma, or m and a. So this is the, so if I write this and I write something, so I write its dimension, it will be the dimension formula of mass. But if I'm writing like this, it's as a whole telling me that it's force. So it is a dimensional equation if I do it like this. Okay? For example, so let me write it clearly. If I write m a equals to mlt minus 2, it will still be dimensional equation, but it will not be a dimensional formula because it has to be a single. Okay? But I could write like this. So this is a dimensional formula of mass times acceleration. I could write like that. Okay. Now we are gonna take a look on some examples of dimension formula. So some examples of dimensional formula. So we are gonna start from the basics. So let's start in, which is the first one. It's mass. So I think it's pretty easy. It's m1 l0 t0, and mass, as it's a fundamental unit, there is no formula that relates it to something else. Even if it does, it will just result in mass, which is defined on its own. Okay. The second is length, m0 l1 t0. The third one is time, which is m0 l0 t1. Is it clear? I hope it's clear. Now, the fourth one is area. So area is, okay, first of all, before writing this, let's look at the most common formula of area. The most common formula is length times breadth. So length is a length, and breadth is also a length. So it will be m0 l2 t0 because it's length square. But if you feel confusion in this, you can also think it like this. In SI system, its unit will be meter square. Meter is for length. As it's for length and there is a square over here, it's L square. But when using this method, don't be confused, because most students I have seen, they get confused in this m and that m. So they see this m and they put m square, which is wrong. Meter is for length. Never forget that. Now, the fifth one I'm going to teach you is volume. So the most common formula of volume is L into B into H, which is meter cube. So meter is length and cube means times 3. So m0 L3 t0. Is it clear? Okay. The sixth one is velocity. So don't worry about the formula right now, because in the other chapters we will learn the formula. We are just trying to find the dimension using the formulas that you might know or you might not know. The most common definition of velocity is displacement per time. Displacement means length, which means meter. Time means second, so meter per second. I could also write this as meter per second. So it's m, l, t, and let's see. Is there any mass? No mass. So it does not depend on mass. If there is a length, 1, and there is a time, -1. So don't get confused in this m and that m. This m is for mass, this m is meter. The seventh one is acceleration. The most common formula of acceleration you will find is v. Acceleration is velocity per time. It is, since acceleration is a change of rate of velocity. We have already found velocity, which is meter per second, and per second, which means meter per second square. So it would be mlt. So let's see. M, does it depend on mass? No. Does it depend on length? Yes, to the power 1. Does it depend on time? Yes, to the power minus 2. Okay, let's do some more. Let's do 8. In 8, we will talk about force. This is very important in this chapter since force is very useful for doing dimension analysis, which we'll learn later. So most common formula that we will find of force is mass times acceleration. Mass meaning kg and acceleration meaning meter per second square. So if I write mlt, so think about it. Kg, so does it depend on mass? Yes, to the power 1. And does it depend to length? Yes, to the power 1. And does it depend upon time? Yes, to the power minus 2. Okay, the next one is 9, pressure. The most common formula of pressure that we will find is force upon area. Since we have always found a force, I'm going to use it directly. So meter per second square divided by area, which is meter square. So it's kg per meter per second square. So if I write its dimension, mlt. Does it depend on mass? Yes, to the power 1. Does it depend on length? Yes, to the power minus 1. And does it depend on second or time? Yes, to the power minus 2. So this is the dimension of pressure. The next one is work. Work or work done. The most common formula of work you will find is F into D. So it's force times distance or displacement. Okay, now, so we know of force, which is kilogram meter per second, and distance is meter. So it will be kilogram meter square per second square. So this is also very important because this is very useful in dimensional analysis. Okay, so it will be, does it depend on mass? Yes, to the power 1, length to the power 2, and time to the power minus 2, because meter square second minus 2. Okay, now let's take 11. The 11th one is power. The most common, we have already talked about power. Power is energy per time, and we found the out. So energy is kilogram meter square per second square by time, meaning let's write second. So it will be kilogram meter square per second cube. So its dimension is m to the power 1, t to the power minus 3, and l to the power 2. You can also write it like this. You can interchange the terms. You can interchange them. So I wrote it like this. It was actually a mistake. I was trying to write 2. I was trying to write L, but since I wrote T, I might just tell you this right now. But generally, write in MLT format because it's easier to check and it's easier to explain. So linear, the next one is linear momentum. I'm not explaining the meaning of all these terms because you will learn them in other chapters, okay? So I'm just trying to show you how to find its dimensions. If you know the formula, you can find the dimension. That's what I'm trying to show you. Okay. So linear momentum, it's also represented by P. So I will at least tell you that. And its formula is mass times velocity. Mass meaning kg and velocity meaning meter per second. So it depends on mass to the power 1, length to the power 1, and time to the power minus 1. I hope it's pretty clear. Next, 13. 13 is torque. Torque, which is represented by tau. It's not a T or L, it's tau. It's a symbol like this. And it's also known as couple sometimes. Okay? So the most common formula of tau is F into R. So I'm writing the most simple version, most simplest version, because I could actually have wrote this as like this. or like this, which is complicated form of the same thing. So I'm writing the most simplest case or most simplest version of the equation because it would give the same dimension. So force is kg meter per second square, and here meter, so which will lead to meter square. So I could write it as m l l square minus t minus 2. Okay, and one thing you must know is I didn't write 1 here because writing 1 and not writing 1 doesn't matter. Okay, and if you noticed, this is the same dimension as work done or energy. So which might give you a clue how dimension may fail or dimension are interesting. Okay, next is 14. It's impulse. Impulse is represented by I. The most common formula of impulse is F times t. So I equals to F times t. F meaning force and t meaning time. So force, it will be kg meter per second square, and time is second, so it is kg meter per second. So it's m l t minus 1. I hope that's self-explanatory. Okay, now 15. So this one might be confusing, so I will try to explain it by my best. I'll try to explain it my best. So if first of all, let's try to find out, and I will tell you something more. The most common formula is Q is I times T. I meaning current and T meaning time. So current is ampere, since current is a fundamental unit, and time is second, so it's ampere second. So you might think, since you only wrote MLT, where is the A? If you remember, I told that there were all 7 fundamental units. It's just that the other were to the power 0, so we wrote them as 1, or we didn't write them. But here, if you see, you can see, does it depend on mass? No. Does it depend on length? Nope. Does it depend on time? Yep, to the power 1. And does it depend to current? Yep, to the power 1. You can also write this as I. Both are common, but I prefer to write it as A. Okay, so now also sometimes you might think you get confused, because when you read current, so I is current, will be taught as charge upon time. So you might think that current is being defined by charge over time, and yes, it is being defined. So you might think, why isn't charge a fundamental quantity? Charge is not a fundamental quantity because it is less useful. Current is more useful as it comes up more. So we are trying to maximize our efficiency. So that's how the fundamental units are made. That's why charge is not a fundamental unit, even though current is described by charge. So current depends upon charge. Okay, the next one, 16. The 16 one we are going to talk about is electric potential. Electric potential. Okay, electric potential. It is also represented by V. The most common formula that you will find is W by Q, which means work done upon charge. So it will be work done means kilogram meter square per second square, and charge means per ampere. So I could write this as kilogram meter square per second square per ampere. Okay, so if I write the dimension, it will be so if I write the dimension, it will be m l square t minus 2 a minus 1. I think it's pretty clear. Oh, sorry. Once I did a mistake. Since charge is defined on Q into T, we just talk about charge which is defined on Q into T. It was actually ampere per second. Do you remember? Sorry, I meant ampere second. So it's actually per ampere second, which will read to T minus 3, which means it's gonna be 3. So I did a mistake. So if you copied it, please erase it. The next one we are going to talk about is electric field intensity, or which is commonly known as symbol is E. And the most common formula you will find is F by Q. F meaning force, Q meaning charge. So kilogram meter per second square by charge, which is ampere second. So it will be kilogram meter per second ampere per second square cube, sorry, um, cube, sorry, minus 3. So if you write this, it will be mlt minus 3a. Okay, the next one, the 18th one, which we are going to talk about, is potential gradient. Potential gradient. So whenever we talk about gradient, we are doing something divided by x dx. Dx meaning it talks about something that changes. So think about this. Think about a plate. It is very dark over here and gets lighter. So we are talking about gradient. We are talking about this. It's getting darker and lighter, and this gives you at the rate how it's changing from dark to light. So think about it. When you use gradient in paint or something else, you find that there is dark and it gets lighter. So using gradient, you can find out how quick or how slow is it transitioning from one thing to another. So potential means dV by dr. R meaning a distance. It is also written as x, and V is for volts or voltage or potential, and D is for a small change, because you're trying to find for a very small change which gives you something that works for everything instead of doing a large one. So here voltage divided by R. So we also did a volt, if you remember, electric potential. So electric potential was kilogram meter meter square per second cube ampere by meter. So we can write this as m l t minus 3a. I hope that's clear. Sorry, it's minus 1 because it's actually minus 1 over here. Okay, the next one, 19. The 19th one is frequency. Frequency, it is represented by F. Its formula, most common formula is 1 by T, where T is the time period. So it will be since time is measured in second, it will be 1 by second, which is per second. So its dimension is m0 l0 t minus 1. Pretty simple, right? The next one is 20, which is angle, which is commonly represented by theta and is measured in a radian, if you remember it or not. This is the plane angle we are talking about. So its most common definition is arc length by radius. So if I take a circle, this length is known as arc length. This is the sector. This is the angle theta, and the this is the arc length. This is the radius, and this is the arc length, because this is called an arc. So if I take this portion is called an arc. So this will be L, arc length, and this is a radius R. So if you see, arc length is measured in meter and radius is also measured in meter. So you see nothing, or you can write 1. Let's write 1. So if I write a dimension, it will be m0 l0 t0, which means that it doesn't have a dimension. So this is also something interesting that you might find. Okay, so there is no dimension over here. Now let's talk about the next one, 21, which is angular velocity. It is commonly represented by omega, and its most common formula is theta by t. Since theta is 1, or it doesn't have a dimension, and time is second, it's per second. So I can write this at m0 l0 t minus 1. So when talking about angular velocity, don't think of it as velocity, because if it were velocity, the dimension will be ml t minus 1, m0 l t minus 1, which is not the case over here. So these are different. So these are not the same. Now let's talk about 22, which is angular acceleration. Angular acceleration, which is represented by alpha. Acceleration was defined as velocity per time. So here it will be defined as angular velocity per time. The is per second by second, which will give you -2. But this is not the unit. We are not talking about the unit of angular acceleration or angular velocity. We are talking about the units that matter in dimension. Okay, think about it. We are talking about units that matter in dimension, because the actual unit of angular velocity is radian per second. Since radian doesn't have a dimension, we have no need for to write it. So think about this as well. So this will be m0 l0 t minus 2. Here it is also not the same as acceleration because the L is different. Okay, now we are gonna go to the next one, which is 23, moment of inertia. Moment of inertia. It is represented by I. The most common formula that you will find is mr square, so mass times perpendicular distance square, mass kg, distance is measured in meter, so this will be the answer. So dimension will be m l 2 t0, or you can just write ml square. Okay, the next one, 24. 24, we are going to use velocity gradient. So if you remember what I said about gradient, gradient is just something with respect to distance or x or r. So velocity can be written as v, and distance will be represented as r or x. So velocity is meter per second. Here the radius or the distance is meter, so we will have m l t. So let's see, does it depend on mass? No. Does it depend on length? No. It depends on time only, so it's -1, and to the power -1. It depends on time to the power -1. Okay, the next one, 25. We are going to talk about coefficient of viscosity. Coefficient of viscosity. The most common formula that you will find is actually complicated. So this you might find complicated right now, but don't worry about it. You can actually get it done. Okay, so try this. This is force, this is area, this is force, this is area, this is velocity gradient. So try it for yourself. Pause the video and try it. I will directly write this one because they are very long. It's not long, but it will take some time, and I don't want to do it. So it's m l -1 t -1. So check if you did it right or you did it wrong. Okay, the next one, 26, is gravitational constant. Gravitational constant. Its symbol is g. Oh, also, the symbol of coefficient of viscosity is eta. It's like a n, but with its longer tail. So longer tail like this. So gravitational constant z. It's, you know, the formula F equals to g mm by r square. We are just using this. So g will be f r square by mm. So try this also. This is also mass, this is also mass, this is distance, and this is force. So you should get the answer of m-1 L cube t minus 2. This question to find its dimension will also appear in the exercise that we do later on. Okay, 27th, which where we are going to talk about capacitance. Capacitance. Capacitance is represented by C. So what's the most common formula, you might ask? We have Q equals to CV. So C means Q by V. Pretty simple. And we have also found of Q and also V. So since you might think how you are going to do this in an exam or somewhere you're not gonna know the dimension of charge and um, charge and potential. Let's see how we will do it. So we know charge is IT, so current into time, and the voltage is potential is work done per charge. So work done per charge. So since this is a charge, it will be IT dot Q by W, and since you know charge is also I, so it will be I square T square by W. So now you can do ampere square. So time is second square by work is kilogram meter square per second square. So you will find the dimension to be MLTA. So let's write the power. Does it depend on mass? Of course it does. To the power minus 1, because this will go up and it will be minus 1. Does it depend on length? Of course, to the power minus 2. Does it depend on time? Yes, of course, to the power 4. Does it depend on current? Yes, of course, to the power 2. So in exam or somewhere you want to do dimensional analysis, you can do it like this. You can break them down into simple formula if you don't remember the exact answer. The next one we are going to talk about is 28, which is specific heat capacity. Specific heat capacity, which is represented by S. We have a formula Q equals to ms dt d theta, let's say that. So, or del theta. So S will be Q by m del theta. Here Q is heat, and heat is a form of energy. So it will have the same dimensional formula or same unit as energy, which has the same units as work done. So if you can correlate, you can think about it, it's actually kilogram meter square per second square. M is the mass, which means kilogram, and delta theta is temperature. And if you remember, temperature is K. So we will have the answer as m to the power 0, because it doesn't depend on mass, 2 T minus 2 K minus 1. K is for temperature because it represented by Kelvin. So this is for temperature, and this is Kelvin. There is a difference. This K and this K is not the same. This K represents temperature in a dimension formula. This K represents a Kelvin in a unit. So this much for today. We will continue more in the next lecture. Thank you.